Good morning, chemistry nerds. I'm thoroughly enjoying my second cup of coffee on this cold slash not snowy day. But hey, let's roll with it. So this is your plans for our alternate assignments for January 8th, 2015. I hope it is the first of all 10 of these that we take advantage of so that we can keep this system rolling for next year. So let's dig into it. So I'm starting off on this cold day with some pictures of snowflakes. So I have a few snowflakes here. You may have heard that snowflakes are individuals. And that is correct. Each snowflake is unique, but they do share some things in common. And Miss Carson's rather insightful comment the other day got me thinking about this, and it relates to what we're talking about in class, that water's polarity determines some things about its structure. So this is relevant to what we're doing. We have here a Lewis dot structure for water, and it gets this bent geometry because of its lone pairs. And both of the bonds in it are polar, and the oxygen is more electronegative, so I've drawn these arrows pointing towards the more electronegative atom. You can think of these sort of as vectors, or like tension that you talked about in your physics class before. One of them is pointing to the left and one of them is pointing to the right, so that cancels out, but both of them are pointing up. So water has a partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. And this means, since it has charges, it can form a crystal lattice similar to ionic structures. So if I add a second water molecule, it's going to want to line up next to its neighbor such that the negative oxygen is on the side with the positive hydrogen. And if I continue on adding more water molecules, they're going to continue in this sort of arrangement. And we end up with a crystal lattice just like an ionic compound. And it's formed because we want this alternating structure of positive, negative, positive, negative. Only in this case we're talking about partial positives and partial negatives. That means that water molecule always has kind of a characteristic crystal. And even though each snowflake is unique, what they share due to this crystal structure is a symmetry. Any snowflake can be divided through its center into 6 segments. So we describe this as being 6-fold radial symmetry. And all snowflakes, even though they're unique in other aspects, all share this kind of symmetry. And if you zoom in, you can see that even on the side branches that begin forming, they also share 6-fold symmetry. So they're sort of like fractals, and this kind of very beautiful structure is underlaid by the chemistry that's behind it. And so every snowflake is unique, but they all share the same symmetry. So if you want to look any more into this, here's kind of an interesting website that explains it in a little more detail. So anyway, tangent over on to what I want you guys to do in place of being in class today. I posted a new video last night, and it is the PowerPoints for what we've been talking about. So I need you guys to go to Chemistry Unit 4, Intermolecular Forces. And this covers all the way back to what we started doing 2 days ago. If you're pretty solid on that and want to skip ahead to just where the new content starts, it starts around the 16-minute mark in the video. But all of it's there if you want to go back and review any of it, or if you want to see some of the pictures that I had drawn up in class, maybe you didn't get a chance to look at them closely. I'm a really visual person, so they certainly help me, and I hope they help you guys visualize what's going on in polar covalent, nonpolar covalent, and ionic bonds. All of that is there in the first 16 minutes. As far as the new material is concerned, this is what I want you guys to key in on. Be prepared to list the 5 intermolecular forces in order of strength. There are 4 main ones and 1 kind of special case. So I don't want you guys to get thrown off when I'm asking for 5, because I've got a flow chart in there that helps you find the 4 main ones. I am looking for the 1 special case. It's called induced dipole. My writing's a little sloppy there. That says induced. So the next time that I see you in class, I'll be asking for the 5 intermolecular forces. There are 4 regular ones and 1 special case, so make sure that you know how the induced dipole fits into the scheme of things with the 4 main ones in terms of strength. Also, I need you to tell me what are the 2 requirements for a molecule to be symmetric. State that in the video, and then use that symmetry to decide if a molecule will be polar or not. I kind of harp on about the fact that molecules may have polar bonds, but that doesn't mean that the molecule in its entirety is polar. So be able to use whether it is symmetric or not to decide if it will be polar. So if you have any questions or concerns, think that I didn't address one of these in enough detail or just need some more things, post anything in the comments. I'll try to be checking those comments throughout the day, at least once an hour, and get back to you. And I will see you hopefully on Friday, and we will start off with these 3 questions and be good to go. Thanks, guys. Enjoy your day off.